metal to metal. Arc welding. A curiously general name for a very specific subject. There are actually many different arc welding processes. Now in this program, we'll be taking an introductory look at the 4 most popular arc processes. Manual metal arc, or stick welding as it's sometimes known, MIG-MAG, TIG, and submerged arc welding. As we'll see during the course of the program, they're quite different. But they also have several fundamentally common characteristics. An arc is created when an electrical discharge occurs between an electrode and the parent metal. A spark is formed, causing the surrounding gas to ionize. This enables a current to flow across the gap, creating an arc. The arc generates heat for fusion of the base metal. With the exception of TIG, or tungsten inert gas welding, the heat generated causes the surface to melt and molten droplets to transfer to the weld pool. Heat input to the fusion zone depends on arc voltage, current, and welding travel speed. So let's look at the processes in detail. First, manual metal arc. Invented in Russia in 1888 and known in the States as shielded metal arc welding, or SMAW. It's the most versatile of arc processes, suitable for welding most ferrous and non-ferrous metals over a wide range of thicknesses. It can be used in all positions with reasonable ease. When an arc is struck between the coated electrode and the workpiece, they both melt at the surface to form a weld pool. The average temperature in the arc is 6,000 Celsius. The job of the flux, which melts instantly with the electrode and the parent metal, is to form gas and slag, which protects the weld pool from oxygen and nitrogen in the surrounding atmosphere. After welding, the slag cools and solidifies and has to be chipped off. The process allows only short lengths of weld to be produced before a new electrode has to be inserted into the holder. The variables which affect the final quality of the MMA weld are current, voltage, travel speed, polarity, and electrode type. So, among the pluses, MMA is ideal for field or workshop use. The kit is very portable and simple, and the process is all positional. On the downside, it requires a high skill factor. It's susceptible to slag inclusions, and it generates lots of unwanted fume. Now, in contrast, let's look at the tungsten inert gas, or TIG process. In America, they call it gas tungsten arc welding, or GTAW. Melting is produced by heating with an arc struck between a non-consumable tungsten electrode and the workpiece. Filler wire is added separately into the molten weld pool. They use tungsten because it has a very high melting point, some 3,400 Celsius. An inert gas is used as a shield to prevent oxidation of the tungsten electrode and atmospheric contamination of the weld and filler wire. So the process variables are welding current, its type and polarity, travel speed, the shape of the tungsten tip, and the shielding gas flow rate. Among the positives, it's ideal for root runs and thin sheet. It produces excellent low hydrogen welds. There's no spatter or slag inclusions. It can be used with or without filler wire. It enables welding variables to be accurately controlled. It can weld nearly all weldable metals, including dissimilar combinations. And finally, the heat source and filler additions are controlled independently. As for the disadvantages, it gives low deposition rates, It demands greater dexterity than MMA or MIG-MAG, and it's less economical on thick sections. It's difficult to shield in drafty conditions, tungsten inclusions can occur, and finally the process has low tolerance to contaminants on either the filler or the base metal. The MIG and MAG processes, that's metal inert gas and metal active gas, are similar to each other but quite different from MMA and TIG. Known in America as gas metal arc welding or GMAW, it's a versatile process suitable for both thin sheet and thick plate. An arc is struck between the end of a continuously fed wire electrode and the workpiece, melting both to form a weld pool. The wire serves as the source of heat via the arc at the wire tip, and it's also the filler material for the joint. The wire is fed through a copper contact tube, which conducts welding current into the wire. The weld pool is protected from the surrounding atmosphere by a shielding gas, which is fed through a nozzle around the wire. The wire is fed from a reel using a motor drive as the welder moves the welding torch along the joint line. So the process offers high productivity, whether it's operated manually or in a mechanized way, such as by robot. In mechanized welding, all parameters are under automatic control, but they can be varied manually during welding. So the variables are welding current, which is proportional to wire feed speed, voltage, the choice of inert or active gases, the travel speed, the tip standoff distance, the nozzle standoff, and the type of metal transfer, dip, spray, or pulsed. Dip is ideal for positional welding and for use with thin sheet. Spray is better for thicker sections. It has a high deposition rate, but is not suitable for positional welding. Pulsed is ideal for applications which fall between the dip and spray criteria. In the mid-80s, a major improvement to the process was achieved with the advent of flux cord and both self-shielded and gas-shielded wires. The wire comprises a metal tubular sheath containing a granular flux and metal powder. So the traditional MIG-MAG process became independent of a separate shielding gas, and this made it more attractive to use in windy field applications. Gas-shielded wires obtain their shielding from a combination of flux and separate shielding gas. Flux cord wires offer high productivity and all positional capability with spray transfer. More generally, the advantages of the MIG-MAG process include high productivity, they're easily automated, they're all positional in both dip and pulsed transfer modes, and they can handle a wide range of material thicknesses. On the downside, however, the welding area does need to be shielded from wind. The equipment is relatively complex, and the process produces high levels of ozone and, in the case of flux cord wire, fume as well. Lastly, to submerged arc welding, or sub-arc, or SAW as it's sometimes known. Unlike MMA, MIG-MAG, and TIG, it's not normally a handheld process. It works by striking an arc between a continuously fed bare wire and the parent plate. The arc, the electrode end and the molten pool are submerged in a powdered flux. The heat of the arc melts this flux in its lower levels and protects the weld from contamination. The wire electrode is voltage controlled to ensure an arc of constant length. The flux is fed from a hopper to form a mound just in front of the welding head as it travels along the joint line. Well, some of the advantages are immediately obvious. There's no spatter or fume, the weld is shielded from the atmosphere, and there are no ultraviolet or infrared radiation effects. Unused flux can be reused, but the use of such powdered flux does restrict the process to use in certain welding positions. Of course, solidified slag has to be removed from the completed weld. SAW is known for its use with high welding currents which produce deep penetration, high dilution, and high deposition rates. Generally, a DC positive polarity is used up to 1000 amps. At higher currents, or in the case of multiple electrode systems, AC is preferred to avoid arc blow. It's also common to use a combination of both, with a DC leading arc. The process variables include welding current and voltage, flux type, travel speed, electrode type, size and extension, flux width and depth, electrode angle, and polarity. Sub-arc welding is widely used in ship and bridge deck fabrication, pressure vessels, line pipe, railway carriages, and just about anywhere that long, continuous seam and fillet welds are required. Well, submerged arc welding just about wraps up this brief introduction to the popular arc processes. To learn more, why not call TWI, which was formerly known as the Welding Institute, on 44 if you're outside the UK, 1 223 899 000. Or why not visit TWI's website on www.twi.co.uk.